a nerd.
My vice better too many times. How's Dylan doing it right now? I don't see that. He looks like he just got stretched today. Yesterday he asked me how to put a bit in my foot and I was like, you can't.
Can you go to the hospital?
No one's talking right now.
Yeah, I think last week.
Oh, my goodness.
A lot of each other.
I went to the first
First one.
You do it left handed?
sure.
Is that
Yeah,
what
I've
you
been
do?
trying it with
None of them seem too interesting.
Oh my gosh, I didn't even notice.
yeah, the
Only two positions.
I just had one of these and I was like curious as to like how crazy it'd be to try and like face the other things.
Yeah. What's the one with something else?
Double H two one. What's your favorite shirts?
It's always
That is
like
the coolest thing ever. I really like that.
it's always like
Right head. Oh, sorry.
Steroids.
yeah, it can be sometimes.
You got challenges?
Yeah, like this.
Huh?
My skin.
Oh.
I'm not working. We're on the machines for 1 hour.
Oh,
You go to like what? Like River or
That was yesterday.
We went to Lake Merritt the weekend we were
so you have to like get up at 12:30 just to go on the machines just like
No,
yeah.
to go to Lake Merritt, we have to meet at 4:45.
yeah.
And for the gym workouts, like 6 o'clock.
4:30 usually.
Or
4:30.
maybe go there.
Uh, Last night, like after class, I was on Sunday.
It's kind of nice though, like going on like a
Yeah.
it's like party.
I don't know. It's about to pick up. I'll do something at work. I'll go to sleep.
Yeah. But then I almost feel like going to bed
I
early
woke
too,
up.
which I guess is good, but it's just like even at that whole first homework assignment was like
My laundry is still.
It was the easy.
yeah, yeah.
Okay, let me quickly hand out the graded homework. Cindy, did you add up the scores as well for each? Because I don't see them. Is it at the end of the paper?
I'm telling you, when did I do that? The scores and
So it's out of 24? Why is your number so low?
yeah.
How did you do the point distribution?
All or nothing.
You already spot that. But I'm like, that's great.
I see. Your scale is just low. That's okay. We can live with that. That's great. Chris, hand it.
After like
Okay, I'm just handing this in so I can get to learn your names. Eric Battenberg. Samuel Branadol. Oh, Samuel. Okay, here we go. Yuan Shi Chen. Okay, Min Ding. Okay, Shu Guan. Okay. David Lynn. See, Alan Gu. Robert Hill. Patrick Blair. I know who it is. Mary Knox. Gary Lee. Howard Lane. Oh. Cassie Young. Dylan Boots. Lucian Sun. Sergey. VJ Law. Jamie Wang. Oh. Cindy, how many homeworks did you collect? How many? How many? Okay, so the homework that you don't pick up, the homework that you haven't picked up will go to Rosita so you can pick it up. So I forgot what the announcement was with regard to the lab. Were they going to email you the pictures? Yes. But some of them have kind of printed it. Is that?
So I will collect the write-up version, and they have to email me the picture and the script in the MATLAB.
Okay. So for those of you who printed it, just email it to her as well. So this is the solution. There's 20 copies. So pick up solution to homework number 2 on your way out. Homework number 3 is on the web. And it has to do with a tomography lab experiment. And Cindy, did you put the files in, or Rosita did? There's an additional file, toms.db, that I couldn't figure out where she got that from. You might want to go talk to her at the end of class to figure out what it's all about. Okay.
When is the homework due?
Oh, right, it's next week. Yeah, due next Friday, the 17th. I hear a lot of sighs. What's the problem? Well, there's no midterm, there's no finals.
Project.
Well, that's going to be very mild. So just so that I have an idea of the show of hands, how many people took 5 hours or less to do this homework? Oh, wow. Excellent. How many between 5 and 10? Wow. How many more than 10? How many just never raised their hands? Like, let's do 0 to 5. Just about everybody. Okay. Okay. Very good. Okay. So that was an easy homework. Actually, I have to warn you, this next homework is harder, so I'll just tell you that ahead of time. That's right. I think if you, from a game theoretic point of view, if you collaborated with each other, you would know what the optimum strategy would be, is that you just collude and okay, we're all ready to go. So what I talked about last time was yeah, this is a copy of last time's lecture, was the notion of difference equations, in particular linear constant coefficient difference equations, and and how they relate to linear shift invariant systems. So I think the best picture we have from last time is this diagram right here. If you can just, thank you. So you start with a linear constant coefficient difference equation, which corresponds to an IIR filter with rational transfer functions. And we showed that we need to have initial condition or boundary condition in order to make it correspond to a system, period. Otherwise, it wouldn't be even a system, because unique input doesn't result in unique output. You need to have that initial condition to be 0 for that system to be linear. And then furthermore, for the system to be shift invariant, you have to make sure the initial condition is chosen in accordance with the input. So as I shift the input and put different kinds of input into the system, in order to make the overall system to be shift invariant, I have to pick the boundary condition or the initial condition of the difference equation to match that input. So in particular, if I have, for example, this kind of a system with an input which is a delta at times n equals 5, then in order to make this a causal linear time invariant system, then I have to make the initial, to begin with, this difference equation corresponds to a causal implementation, which is y of n takes on the value of a times y of n minus 1 plus b of x of n. Or it could have an anti-causal interpretation, which is y of n minus 1 takes on y something times y of n plus something else times x of n. So the causal implementation, let me just write that for completeness. So for this causal implementation to correspond to an LTI system, if the input is non-zero up until the time is n equals 5, I have to pick the initial condition to be the output at time 4 equals 0. If this was delta of n minus 100, then the initial condition would be y of 99 equals 0. It has to be 0 here to make it linear. It has to be picked at the right time to make this shift invariance. Otherwise, you can go through, if you make the initial condition, let's say for this system, make y of minus 1 equals 0, you can come up with a solution, but you will find that if you shift the input, the output doesn't shift. And the way to do that is go through solving the entire ragamuffin of this difference equation. I don't want to do it because it wastes a lot of time, because this is not a course on difference equations. But you can see, if I pick the wrong initial condition, and if I shifted the input, the output wouldn't be the shifted version of the input, which is a condition for shift invariance. And furthermore, for the anti-causal implementation of that, which is written by here, again, I have to match the input with the initial condition to match the input. In particular, if the input is, again, delta of n minus 5, which is x of n looks like this, it has a kink at n equals 5, then the initial condition has to be chosen that y at times 5 equals 0. And the reason for that is shown here, because you want to be able to compute you want to be, let me just draw it here, because once y of 5 is equal to 0, then I can plug in and compute y of 4 using y of 5, y of 3 using y of 4, y of 2 using y of 1, y of 2 using y of 3, etc. I can go backward in time. Does everybody see this point? Okay, and you can also generalize that even further. You can say that if the system was, let's say we're talking about causal system, but what if it was a second order difference equation? In other words, y of n was taking on the value something times y of n minus 1 plus something else times y of n minus 2. What would be and we want it to be causal, what would be the boundary conditions? First of all, because it's a second order difference equation, we have to have two boundary conditions, right? And what would the two boundary conditions be? Well, it would be, let's say the input was n equals 5, it would be y of 4 equals 0 and y of 3 equals 0. Because you need to go 2 time steps back in order to compute a particular output point, right? But what I want you to walk away from, I mean, this is really not a course in difference equations, but the reason I did all of these things is, in order to generalize this to 2D, there's a simpler method, and that applies to 1D and 2D. So let me explain what I mean by that. So So in the so generalizing, so boundary condition for two-dimensional different linear constant coefficient difference equations. This is kind of the goal for today's lecture, or at least part of today's lecture. Um, what we talked about last time was that if you have a two-dimensional linear constant coefficient difference equation, then we talked about the notion of recursive computability. The output mask has to have a wedge support for the thing to be for the system to be recursively computable. Now what we want to talk about is, in addition to that, we have to pick the right boundary condition in order to do that. And how do we pick that boundary condition? And the answer, so in other words, how to choose the boundary conditions for 2D LCCDEs. And the strategy we're going to take is generalize the way we compute the boundary condition in a one-dimensional system into 2D. So approach is really generalize the approach in 1D. Well, you might say, well, what do you mean by that? Well, let me again do an example. Suppose that I have a realization of a one-dimensional difference equation. Y of n is just y of n minus 1 plus x of n. Okay? And in general, how do we pick the boundary condition for this? Well, so this is a causal system. Okay? So if I have an x of n, an input to this system, that becomes non-zero at time n naught, okay, then we all know that the boundary condition would be that output at time n naught minus 1 has got to be 0. Okay, so to obtain a LTI system, because of the discussions we had in the last time's lecture, the boundary condition should be y of n naught minus 1 has got to be equal to 0. And again, we're adjusting where the output is 0 to the time that input becomes non-zero. And another way of arriving at this conclusion is to take the following steps. Is compute the region of support of the output given the difference equation. And then number 2, set the boundary condition and call the region of support of the output to be R sub y. R stands for region of support, y is the output because output is denoted by y. And then set the boundary condition to be equal to 0 outside of R sub y. Okay? And how do I do one, and what do I mean by step 1, step 2? Well, here's the way I compute the R sub y, the region of support of the output, is to start with the region of support of the input and the region of support of the impulse response, and then from that deduce what the region of support of the output is. So making this a little bit more detailed, if you can roll up just a little bit. So more detailed version of that two-step procedure is to, so this is detailed. You start with region of support of the input, which we call R sub x. Given the fact that we've nailed down what the computational procedure is, or what the realization is, we're no longer dealing with just the difference equation. We know which implementation or which realization of that we're working in. So given the computational procedure for our difference equation, we know we can now compute the impulse response, h of n, and then from that we can compute R sub h, which is the region of support for the impulse response. Okay? And then using step 1 and 2, use R sub x and R sub h to compute R sub y, which is the region of support of the output. And then the boundary condition has to be equal to 0 uh, uh, for all n that are not in R sub y. Okay? So this might sound like a hell of a lot of steps to go through for just a one-dimensional difference equation. But indeed, if you think about it, that's exactly what we do in 1D. And that's exactly what we have to do when we go to 2D. The simple arguments of causal, anti-causal, therefore just said y of n not minus 1 equal to 0, that all of that intuition doesn't carry straight forward. The best way to think about it is to say, what is a bigger, more generalized methodology for 1D? And this is it. And now translate this methodology straight on to 2D. But before I translate it to 2D, I want to convince you that indeed it works in 1D. So let's just do that through this famous example that we have, which is, y of n takes on the value y of n minus 1 plus x of n. So let's go through that. Can you zoom up a little bit, please? So actually, let's go through that example. Y of n takes on the value y of n minus 1 plus x of n. So this is a causal system, and you're given x of n is delta of n. Okay, so what I need to compute is R of y. In other words, what is the region of support for the output? Well, it's not that hard to figure that out. If x of n is delta of n, then y of 0 takes on the value y of minus 1 plus delta of 0. And then y of 1 takes on the value y of 0 plus 0, because input at time 1 is equals to 0. Y of 2 takes on the value y of 1. Y of 3 takes on the value y of 2. On and on. And so, based on this, it seems like the only time is and also if you look at y of minus 1, it takes on the value y of minus 2 plus 0, etc. So if I look at these things, the only time anything is non-zero and has a shot at being non-zero is right here at y of 0, because that's the only point where we got delta of 0. That's non-zero. So definitely, if I were to write down the region of support for the output y of n, it's definitely going to be non-zero at index 0 right here. It's going to be something else. And once this is non-zero, once y of 0 is non-zero, it makes automatically y of 1 non-zero, y of 2. These are all some non-zero values. And these guys, on the other hand, have no chance of getting any input contribution. So y of n is going to have a region of support that looks like this. So this is R sub y. This is the region of support of y of n. And therefore, the boundary condition has got to be equal to 0 for all these negative indices, minus 1, minus 2, etc. So this is the boundary condition that makes this computational procedure to correspond to an LTI system. Alternatively, we can even go one step beyond that and do the thing in a more detailed way. You can compute h of n. What's the impulse response for a system like this? Well, you can do that by writing down the z transform. So solitaire, another way of looking at the same thing. What's h of n? Well, you can just take the z transform. You get y of z is equal to z inverse y of z plus x of z. And you can write down h of z then is y of z over x of z as 1 over 1 minus z inverse. That means h of n is just u of n. So you can say that this is R sub h, the region of support of the impulse response. And if this is the region of support of impulse response and the input is x of n, is delta of n, it's just non-zero here, then convolving these two things in your head, you can easily see that the region of support of r sub y would be here. So this is r sub y. And therefore, the boundary condition is going to be 0, right in this region. Okay? Is this clear? So you can, it's quite easy and it's quite clear what happens in 1D. And now we're just going to extend this procedure right on exactly that same steps in 2D, to 2D. Okay? So let's just do that. So what happens in 2D? Well, it's exact same steps. In other words, given the computational procedure, determine R of H, given input, determine R of X, and then using R of X and R of H, determine R of Y, and then boundary condition is equal to 0 for all n1 and n2s not in R sub Y. Those are the same kind of steps that we take. So let's kind of define that let's just go through an example and see if we can take these steps one after another. If you can roll up so half of the other page is shown. Thank you. So let's just do an example here. Suppose I have a difference equation. Suppose I have, a computational procedure which is as follows. Y of n1 and n2 takes on the value minus 2 y of n1 minus 1, comma n2, minus 3 y of n1, comma n2 minus 1, minus 4 y of n1 minus 1, comma n2 minus 1, plus x of n1 and n2. So right off the bat, let's draw. It turns out to do these steps in 2D, one of the things that helps you a lot to do this intuitively is to write down the output mask or plot the output mask and the input mask. So in this case, the output mask is given by to compute y at times n1 and 2, I need n1 minus 1, comma n2, which is this guy, n1, comma n2 minus 1, which is this guy, and then n1 minus 1 and 2 minus 1, which is this guy, and the input mask obviously is this. And you can go through kind of multiple steps and multiple arguments, but you can show if the output mask is like this and the input mask like this, then the region of support for R sub H, for the impulse response, you can plug this into the difference equation and convince yourself that R sub H would look something like this. As a function of n1 and n2, it'll be non-zero for this whole region. In the first quadrant. Okay? In general, the way you do it is you start with this and you kind of flip it over. And I'll show you a few other examples. So by the time we're done with the lecture, by the time you do the next homework, which is due the 24th, you develop this intuition. But the trick is very simple. I'll give you a few other examples to see how you can quickly go from output mask to R sub h. But here's the kind of intuition, and you can prove yourself that this is the R sub h for this by kicking the system with the delta and computing the outputs and convincing yourself these are the only non-zero values that you get. So if the output mask is like this, then the way you do it is you flip it over this way, and this becomes the R sub h for the region of support for the impulse. Okay, so here's R sub h, and now suppose that I kick this system with an input, which looks like this. This is x of n1 and n2, so it has this kind of a region of support. For simplicity, I've just made it be just a 3x3 input. And again, without doing the actual convolution, the same way as in one dimension, you can do the convolution in your head just to know what the region of support for the output is. You can convolve this in your head with this R sub h, and in order to figure out that R sub y, the region of support for the output, is going to be one index to the left. Because this is one index to the left, is going to be all these points. And I'm running out of patience, as you can see. So it's this thing. So this is R sub y. Okay? And therefore, the boundary condition is going to be out. So this is the boundary condition. It's going to be 0 for all these values of n1 and n2. And given that, now we can now apply. Given this fact, this is the boundary condition, and given the fact that this output mask is recursively computable, we can now compute, using these boundary conditions, we can compute the output points in a recursively computable way. I want you to see this output mask. So given that this output mask has a wedge support, this angle is less than 180 degrees, and given that now we have this beautiful boundary condition, you can compute the output points one after the other. You can do it row by row, or you can do it column by column, and you can even do it in a zigzag manner. There's many different ways of doing the output computations, one after the other. Are these steps clear? Let me do one more example, and in order to avoid writing down so many things, I'm just going to use Eennlb's pictures and Eennlb's books, just so that we can move a little bit faster, so we can move on to the discrete Fourier transform. So what I'm going to cover is the example on page 98, 99, and 100. So page 98 to 100 of Eennlb's book. So here's what we've got there. We've got this difference equation. If you can zoom in, please. Thank you. Okay, and maybe you can focus just a little bit. Much better. Okay, I think it's focused enough. So here's our system function. This is the so h of z1 and z2 is the ratio between y of z1 and z2 output and the input z transform. And you cross multiply y's by x's. You take advantage of the shift property in order to come up with the difference equation. And now this difference equation can have 4 different implementations, and those are shown here in equation. No, you don't all adjust. You just stay where you are, the camera person. All right. Well, if you both move, then we both miss each other. So this is one realization where we just take this point to the left-hand side, shown here. And this is a second computational procedure This is the third one, and this is the fourth one. And I think we already went over that just a little bit last time. And we already know, for example, how from this computational procedure to come up with any one of them to come up with input-output mask. Here, you have n1 minus 1, n2, n1, n2 minus 1, n1, n2 minus 2, and x values. So here we go. This is the output mask for the first realization and the input mask for it. This is for the second, this is for the third, and this is for the fourth. And of these four, let's go over and collectively decide which ones correspond to a recursively computable systems and which ones don't. So does this one correspond to a recursive? Yeah, it certainly does. If I draw a point here and I draw a point here, the angle here is 90 degrees. So this is recursively computable. And while we're at it, what do you think the R sub h is? The region of support of the impulse response of a system corresponding to this realization. Well, this also has a 90-degree thing, so it's going to have an R sub h that's, if I extend this way and this way, it's going to be an R sub h that's in this region, which is shown right here. Okay.
How do you determine that? It just seems really arbitrary to just say, oh,
Flip it over. Oh, once for the first time, you have to go through the actual difference. It's pretty painful, but you have to plug in delta of n into the difference equation. Yeah, do it by hand. And Eennlb goes through the pain of explaining all of that. But you only have to convince yourself once, and then from then on you'll see, oh, that's the rule you have to kind of apply. Okay. Then you move on to here. This is the second. This is the computational procedure for the. This is the input-output mask for the second computational procedure. And now what you do is I have to draw a line connecting this to that and extend it here and extend this line here, and the region of support would be there. Let me draw it. It makes sense for me to draw that and explain it a little bit better. So if the input-output mask has a region, if the output mask has this region of support, because I don't want to write on the book, I'll write it here. So what we do is you connect this guy to this guy, and then extend it here, and connect this guy to this guy, and extend it here. I usually actually, this is the first time that I discuss this trick, if you will, in the lecture. Usually I let the students discover it in the homework, or by just reading the book, but I think it's better to be upfront and not hide anything from you. So then this would be the region of, this would be R sub h, where there's a second point there, there's a point here. Yeah, there's a point here, there's a point here, and then so this angle essentially is the same as this angle. Okay, and again, this is shown, the region of support for this R sub h corresponding to this system is shown here. Okay, and finally, for the third realization, we have again a wedge support. This angle is definitely less than 180 degrees, and now R sub h would be a straight line this way, so it'll be a wedge region here. And sure enough, if you go through it, you'll see that it's a wedge here, except that it doesn't include 0, 0. And finally, we come to the fourth system, which is here. And what can we say about the support of this output mask, or recursive computability of this? This is not recursively computable, because if I start from the center point here and draw a line here and another line down here to encompass all the points, I end up getting 180 degrees. So because this is not a recursively computable system, there's no boundary essentially there's no boundary condition that will ever make this thing work. That's what the implications are. Make it work, I mean to compute the outputs in a recursive way, one after the other. For a system like this, you might have to solve implicitly a big linear system of equations in order to figure out what the output is going to be. But certainly you can't compute it one after the other. Okay, any questions or comments? I'm going to talk about one more thing on this material or chapter, and then move on to the next topic, which is discrete Fourier transforms and ways of computing it. So suppose that um, I've been given, as an example, I've been given a given difference equation using the same ideas that was talked about, and I wanted to come up with a particular realization such that the impulse response is third quadrant. Okay, so I'm given this difference equation, y of n1 and n2 is y of n1 minus 1, comma n2 minus 1, plus x of n1 and n2. This is a difference equation, and I'm been asked to find the computational procedure so that the h of n here is third quadrant. Okay, and based on what we've learned or what we've discussed, how would you go about solving a problem like that? Well, there's no more than two different possibilities here, right? No more than two computational procedure. Either this takes on the value of that, or you bring this to the left-hand side and this takes on the values of those other ones. So, and then what you can do is you can write down the input-output mask for both of those, and then based on that, figure out what the region of support for R sub h is, and that only one of them is third quadrant. So, so there's only two computational procedure. Number one is just y of n1 and n2 takes on y of n1 minus 1, comma n2 minus 1 plus x. In this case, the output mask as a function of n1 and n2 looks like this. And if you go through a bit of a calculation, what you find is R sub h as a function of n1 and n2 would have this kind of region of support. Non-zero along this point. So this is the first quadrant support. That's definitely not the procedure we want. On the other hand, if you pick the other computational procedure where this one takes on the value of these other two guys, so we get y of n1 comma n2 taking on the value of y of n1 plus 1 comma n2 plus 1 minus x of n1 plus 1 comma n2 plus 1. Okay. Then what happens is the output mask as a function of n1 and n2 would look like something like this, and if you compute the R sub h, the region of support of h, you find that it's the flip version of that. It'll be non-zero for these points. So this is indeed a third quadrant impulse response. So essentially, by picking the right computational procedure, you can make, very similar to the 1D case, you can have different regions of supports and different impulse responses. So to wrap all of these things up, the picture, the mental picture I want to leave you with, is this clear? Is this discussion clear? Yeah, was there a question? I see some puzzled faces. Like Sam, it seems that you're a little bit puzzled. Oh my God. Okay, next time I should come into class. I'll pop up a pill of Ritalin. I don't know if you guys heard about the news about the stimulants. Did you hear about that? Yeah, apparently in college campuses, people use stimulants. Like in my generation, when I was at Caltech, the thing to do is to have caffeine pills. You pop one in, it's like 100 times more effective than Mountain Dew. It keeps you up all night. But the stimulant things apparently is even better from what I hear on the radio. But so some kids pretend like they have learning disability or ADHD or whatever, AHD. I can't remember the name of it. They go to the doctors. They've learned all. They've looked up the symptoms on the web or somewhere. They pretend they have it. They get the prescription. They use it. They use some of it themselves, and then they start selling it to the rest of the students, especially at the time of midterms and finals. So anyway, just thought I would pass that on. I just come to the class, and as I hand in the homework, here's a pill.
Just giving us business ideas.
What?
Just giving us business ideas.
Well, this is not a business class. This is a signal processing class. Okay, so your type. But does everybody follow what I'm doing here, or is it pretty clear? Okay. So the final picture I want to leave you with is that. In general, the h of z plus region of convergence uniquely specifies h of n, an impulse response, and these two things uniquely specify a computational procedure. So if you know this, you can go here. If you know this, you can go there. So there's a two-way arrow from all of these things, right? So a difference equation by itself is not enough to specify h or h of z. The same way as h of z by itself is not enough to determine uniquely what h of n is and what the computational procedure is. So there's an ambiguity. Without region of convergence, h of z has a certain amount of ambiguity. The same thing, a difference equations without knowing what computational procedure you have has a certain amount of ambiguity. Neither difference equation nor h of z by itself is enough to uniquely specify what the system is. Okay, so and you can clearly show yourself in 1D and 2D and any dimension that a given h of z with different regions of convergences would correspond to different computational procedures and therefore different h of n's. So for example, h of z plus ROC1 could correspond to h1 of n, and furthermore could correspond to computational procedure 1. And then h of z plus a different region of convergence could result in a different impulse response and a different computational procedure. So unless you nail what the region of convergence is, you haven't really, or unless you've nailed what particular realization of a difference equation you want to use, you can't really tell what's going on. You can't really tell what the system is. You don't know what the impulse response is. Okay, that's the end of discussion on whatever chapter it is in Eennlb's book. I think it's chapter 3 or so. We're not covering stability or any of that kind of stuff. So next, I'm going to move on to DFT because DFT is the one transform that's used in practice, and that's kind of the next chapter. We won't go over all the pieces of chapter 4 in Eennlb's book either, but just kind of a cursory look at the important parts of it. So we're going to talk about two-dimensional DFT. But before we do that, I want to just write down the expressions of all the transforms so that you can place DFT in the right context in your brain, so you know where it stands with relates to all the other transforms that are happening. So to begin with, you start with a discrete time, and I'm only worried about discrete time signals. And I do it in 1D, and then we'll move on to the two-dimensional version of it. So there's a transform called DTFT. That's the thing that we talked about at the beginning of the class. How do I reconstruct from the phase of the DTFT? How do I reconstruct from magnitude of DTFT, etc.? And this is a function of, this is written, DTFT is written by x of omega, which just is a continuous variable. And this is discrete. Summation over n of x of n e to the minus j omega n. Then there is a z transform, and that this omega guy is a continuous variable, and it's real. X of z here, z is a continuous variable, but it's complex. Okay, and it's written as summation of x of n z to the minus n. And now, so what's just off off the bat, what is the problem with DTFT and Z transform? They're what? What's bad? Yeah, that's exactly right. I mean, you can't compute in a computer. You can't compute things. You can compute samples of x of omega, and you can compute samples of x of z. So first of all, we all know x of omega is x of z computed on a unit circle, right? So those two are related. But the problem with both of them is that these are continuous variables. So instead, we come up with a DFT, discrete Fourier transform, which is x of k summation over x of n e to the minus j 2 pi nk over n. And now this is an integer, and it takes on discrete values. So for the first time, we have a transform that takes on an array of numbers and spits out another array of numbers. And from this, you can get back x of n as you wish. And for those of you who have forgotten some of your DSP, there's a thing called FFT. It stands for fast Fourier transform, and we talk about that. And FFT is just a method. It's just an algorithm to compute DFT. You can compute DFT 5 different ways. You can do it in a direct way, or chirp Z transform way, or FFT way, or what's it called? There was a famous technique that was popular in the mid-'80s. Not the prime number one. It never took off, even though mathematically you could show it had lower number. Anyway, it's just a method to compute DFT. Just as a little joke, once I ran into my advisor Oppenheim at the dining hall at MIT with his son Jason, who at the time was maybe 5 years old. And somewhere in the middle of the lunch, I asked Jason. I said, "Jason, what does your dad do?" He said, "He does FFTs." So that's a 5-year-old picture of what his dad. Well, apparently, I mean that must be the one thing you talked about at home is FFTs. Actually, I never asked that question from my son when he was 5. If you ask my son now, I say, "What does your mom and dad do?" "Oh, they're just nerds." Categorically. Okay, so so just pictorially, this is the Z transform. X of omega. So x of z is defined in this z plane, real part of z and imaginary part of z, and x of omega. So it's a two-dimensional function, complex value that you can think of as sticking out of this plane. It has a value everywhere in this plane. And if you took I always called it like a birthday knife, and cut like a cake, you cut a circle around it. The values of the cream that you get on top of the knife as a position of the knife moving around, or the heights variation as you move around, that's x of omega. And finally, x of k is just x of omega evaluated at uniformly spaced values of along the unit circle. So it'll be, for an 8-point transform, it'll be here, 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 and here. So x of omega is equally spaced samples on the unit circle. Okay, so the key question that comes up in 2D is, well, in 1D we have this fantastic algorithm FFT that computes the Fourier transform of signals very fast, and in 2D there's two ways of computing two-dimensional FFTs, either as a series of one-dimensional FFTs, which is called row-column decomposition, and it's not that different from when we talked about convolving a separable signal with a signal with a impulse response that's separable, or you can apply a genuinely two-dimensional fast Fourier transform algorithm, which does the decomposition fundamentally in 2D. And I'll talk about both of those really briefly, and you'll see that the computational cost for those are comparable, although the genuine two-dimensional DFT has a slightly lower computation cost, but more complex to implement. So basically, this part of our course has to do with computational complexity of computing 2D DFT. So what is 2D DFT? Well, you compute DFT of x of n1 and n2, or you define it as a double summation of n1, n2, x of n1, n2, e to the minus j 2 pi n1 k1 over and capital N1, and then e to the minus j 2 pi n2 k2 over capital N2, where we're assuming this signal is n1 by n2 points. And this is for k1 and k2 between, sorry, k1 small in between this range, and k2 is smaller than n2 and 0, but it's 0 otherwise. So DFT is not defined for outside of these values of k's. And then the inverse DFT is x of n1 and n2 can be obtained back from x of k1 and k2 by the following summation: 1 over n1 and 2 of x of k1 and k2 e to the j 2 pi k1 n1 over n1 e to the j 2 pi k2 n2 over n2. And this is for, again, n1 between capital N1 and 0, 0, and n2 between capital N2 and 0, and it's 0 otherwise. Okay? It's a lot of summation for nothing. I mean, it's not for nothing. It's just the same thing as 1D, but just extended to 2D. So when we were dealing with one-dimensional signal processing, if you wanted to convolve two signals, let's say you have an input signal x of n that has m non-zero points, and you have a impulse response h of n that has n non-zero points. And why was DFT useful? Because you can use DFT to do convolution, right? So DFT relates to linear time invariant system, at least not the IIR ones, but the FIR ones, because you can compute the DFT of impulse response, you can compute the DFT of the input, and multiply them together, you get the DFT of the output, and then you can take inverse DFT of the output to get the a y of k, the product of those two things, to get the output. Everybody familiar with that? Right? Seen it all in signals and systems, right? So let me kind of quickly flash this by. So use of DFT in convolutions. Okay, so if I have x of n going into a LTI systems, y of n coming out, and this guy is n point, and this guy is m point, then output is going to have n plus n minus 1 points. Then as long as we choose p larger than n plus n minus 1, then we can apply the following steps to compute the output from the input. Number 1, compute the p point DFT of input. Call that x of k. And what do we mean by a p point DFT of input? If the input has only n non-zero values, how do I compute its p point DFT? Pad it with a bunch of zeros until it's p points, right? Number 2, compute the p point DFT of h. You get h of k. Number 3, compute h of k, x of k times h of k to get y of k. And this is DFT of the output y of n. And then therefore number 4, this is using the convolution property of DFT. Take the inverse DFT of y of k to get y of n. So again, this is just a reminder. So of what's going on. So if I pick p to be incredibly larger than n plus m minus 1, let's say n plus m minus 1 is 100, and I pick p to be 200, is this method going to get messed up? Yes? How many people think yes? How many people think no? Correct. It won't get messed up because the 100 of the points will be 0. Okay. In real life, when you want to do FFTs and stuff, there's certain advantages to be gained by using powers of 2, and therefore, many times even though n plus m minus 1 might be just a random number like 100, you pick p to be let's say 128, just so that you can have a fast method of computing the output.
Why do you want p like greater than n plus m minus 1? Can it be equal?
Oh, greater than or equal. Thank you. Very good. Very good. In the spur of the moment, yeah, it can be exactly equal. Okay. So in 2-dimension, the same thing holds true. So if I have an m by n, so let's just write this down. If I have an m by m input and n by n impulse response, the output is n plus n minus 1 times n plus n minus 1, and so I can apply the same kind of things to compute the output. So all of this applies in 2D. So the only caveat is, how do we compute the 2D DFT in 2 dimensions? You can roll up just a tiny bit. Okay, so the question is how to compute 2D DFT. And there's basically 3 ways of doing it. And again, remember, this is the expression of our 2D DFT, right? How do we compute that? Well, there's the direct method, just like in 1D. And the direct method works by for every value of the output, x of k1 and k2, this is x of k1 and k2, you multiply this by these exponentials and add them up, and that's called the direct method. And then the second method is row column decomposition. And the third method is vector radix, which is really this is the true equivalent of FFT, but in 2 dimensions. And why do I care about computing 2-dimensional DFTs? Why do I care about computational complexity of it? And what are some factors that determine computational complexity of anything? Yeah, let me ask that question. When you design an algorithm, what are some factors that determine computational complexity of things? How do you measure? You have approach A and approach B, and you want to say this one costs more in terms of, and you're implementing it. Yeah, go ahead. Good. So one most immediately. So here's the factors that affect speed. The thing that immediately comes to mind is number of arithmetic operations. That could be multiplies, adds, or whatever. And for the most part, traditionally when we teach signal processing, we've kind of been emphasizing that. What other thing in practice comes into play? Exactly. So there's two memory requirements, right, Alan? There's the usage of memory as the program goes along, but also the size of the code itself and the complexity of the code. Is it 5,000 lines of C program to do this matrix inversion, or is it 10 lines or 100 lines? So complexity of the program itself. So memory, or the space for the executable, and a lot of times that's referred to as footprint, right? And the other one is the memory it uses, and it has a name. The computer architecture people use a different name for that. It's called what? The leap memory? Anybody we have from computer architecture in this class? No. Okay, so memory usage as it has a word for it, as the program moves on. So let me give you an example. So why is it that the size of the footprint is important? That's the size of the executable. You've written your C code, you've compiled it, you do ls minus l on your Unix machine to see how many bytes does that executable take. And why is that an important measure? Because let's say for people who have cell phones, for example, if you're downloading an application over the air from Verizon, you don't want to wait half an hour just for the executable to get to your phone. You want it to get there in 5 seconds. It's, we live in a society of instantaneous gratification. You can't wait 10 minutes. You want to play that video game now on your cell phone and can't wait too long. So and almost all these complexity arguments had gone away for a long time until the cell phone and wireless industry came. Now it's important again. How about usage of memory? Again, the cell phone has very limited memory. And what would be some applications where usage of memory is prohibitive? Video. If I'm doing motion estimation, I have to store 2 entire frames in order to search for the best motion, and then even at the decoder, I have to, when I'm doing predictive coding, I need to know what frame n-1 is, because I receive the difference between n and n-1. I decode that difference after it's been Huffman coded, etc. And then I have to add it to frame n-1 to reconstruct frame n. That means I have to have I have to have storage for 2 entire frames. That's a lot. If your pixel size is 200 by 200 and add it up, it's 24 bits of color, and that n-1 frame also you have to store it in the not in the compressed format but in the uncompressed format, which is hell almost. So that's the amount of usage, the memory that the program uses as it goes along, and those are important as well. Most recently, one of my grad students, Pierre Garrig, is working on sparse Bayesian learnings for overcomplete or sparse representation of signals. And so essentially the problem is you have a dictionary of functions and you want to come up with the dictionary is overcomplete, and you want to find a linear combination of those dictionaries that approximates the signal best, but you want that linear combination to have as few coefficients as possible. So there's norm 1 minimization, norm 2 minimization. This is L0, norm 0 minimization. You want to have as few coefficients in your representation of your signal given a dictionary. It turns out to solve that problem accurate or properly, you need to do matrix inversions. But if you have an image that's, let's say, 1,000 by 1,000, the matrix you have to invert is 1,000,000 by 1,000,000. Kind of like the reconstruction from magnitude thing, right? If your image was n by n, the matrix you had to invert was n squared by n squared. So when you look up the matrix inversion literature, what happens is that up to a certain size of matrices, it turns out if you got a 10,000 by 10,000 matrix on today's fast machines, like a single processor, you can do it in 10 minutes. But the operation count goes up as n cubed. So if the size of the matrix becomes double, the computation becomes 8 times bigger. But the size of matrix, but if I double the size of my image, if I have a 100 by 100 image, make it 200 by 200, the size of my image went up by 4, and therefore my computation goes up by 64. Okay, so instead of 10 minutes, it takes 640 minutes, which is 10 hours. That's a whole day. So you can parallelize things. But anyway, the reason I got into this discussion is that there's the computational complexity that goes up. But as it turns out, when the size of the matrix goes up, the I/O becomes a killer as well. Just getting when the computer is doing calculations, the numbers get stored at 3 different levels. There's the cache, then there's the memory, then there's the disk, and then there's the that's right. So there's memory and disk, and so you don't want your machine to get into paging mode where doesn't have enough space in cache, therefore it puts it on the disk, and so you spend a lot of time reading back and forth from the disk. That already slows you down. That might become the dominant factor in how long the whole thing takes. Not how much computation. On how much computation, we have a good handle on a lot of algorithms. O of n, O of n squared, O of n cubed. We can calculate that easily. But for a given architecture, for a given machine, if you exceed cache limitations or memory limitations of it, you can get into factors like paging, and those we don't really have a good handle on. Those become much more computer architecture fine-tuning kind of issues, and you have to make sure that they don't at the end kill you, right? Okay, how about the third factor that we as signal processors we always ignore in terms of what affects complexity? It's just the language you write the code. So how many of you have programmed in Java? Good. How many people have programmed video algorithms in Java? None, because it's so damn slow. It just tests your patience. If you implement anything in Java, it's 10 times slower than if you implement it on C, in C, for example, right? And what are some techniques, if you're just using computers, what are some techniques to speed up beyond C implementation? Assembly, that's it. And a lot of software engineers in industry spend a lifetime. I optimize this and I optimize that. What does that mean? Is you figure out, like, for example, Intel, when they release their chips, they have MMX instruction sets that is pseudo-assembly in order to help developers who are doing video applications implement their stuff faster. So it does, I don't know, vector multiplications, inner products fast. It does matrix by vector multiplication fast. It does block matching for motion estimation fast. So, and how do you get that speed up? You're not writing it in C. They have already optimized it at the assembly level, and then they've provided API for you to call those so that the time-consuming operations get done very fast. And by the way, for chip companies like Intel, who keep doubling the speed of their chips, but they're kind of running out of applications as to how do we now sell the new product we got? Okay, now we got 4 gigahertz chips, but how do we convince the corporations that bought the 2 gigahertz machines last year, now they have to upgrade? And so how do you think they convince them? What application is ideally suited for that? Video, because it's a lot of data, it's a lot of computation, in particular video encoding, because that's video encoding and decoding, and most times are very asymmetric. Video encoding takes hundreds of times more than decoding, and so, like, I would visit Intel, I don't know, 4 years ago, and they would say, "Oh, well, Professor, we want to show you something we've done," and they take you to a room and say, "No, we can real-time encode I don't know, 500 by 500 pixel video real-time on our latest, I can't remember, latest Xeon 2.4 gigahertz." And I bet you if I visit them today, they're not going to show that same demo. What would they say? "Professor Zakor, we now can encode real-time on a single Intel chip an HDTV signal," right? So, I don't know how we got sidetracked into that, but anyway, the speed of the thing also depends on the language and the platform and the thing is run on. And for years and years, the signal processing people would go to conferences and they would come up with tweaks on FFT. Oh, they said instead of n log n, now I have n log n minus 3. And then the next guy would go, "Oh, now I have n log n minus 3.5." And everybody would clap for them. And once my office mate, what's his name, Webster Dove, who by the way, whose wife Monica Dove was the assistant to Oppenheim. He stood up and he said, "Look, I can speed up the whole thing by a factor of 10 if I just coded in assembly." And everybody looked at him like he was crazy, but he was right. If you don't code in C or if you don't code in Java and use a different programming language, you can of course get huge amounts of speed ups. Okay, so given this picture of the different methods of computing, if you can roll up just a little bit, of DFT, let's just now stare at this and try to come up with direct method arithmetic count. So this is it. This is the direct method equation. So for each k1 and so for each value of k1 and k2, how many multiplications do I have to do and how many additions do I have to do? This goes from 0 to n1 minus 1, and this goes from 0 to n2 minus 1. But for the sake of argument, we're assuming n1 is equal to n2 is equal to n. Well, there's n squared values of this that we have to go through. So roughly speaking, we need n squared mults and n squared adds. And how many k1s and k2s are there? How many values of k1 and k2 is it? Well, it's n by n, so there's n squared of those. So putting these two things together, roughly speaking, we need n to the 4 mults and n to the 4 adds. So in many practical situations, it's very important to know how your complexity goes up as n, where n could be size of your image or the size of your matrix, etc. Okay? So the next method we're going to talk about is row column decomposition. Does everybody follow that? The next column is row column decomposition. I'll start on a new page. And what row column decomposition does is the best trade-off between computational complexity and ease of implementation. The code for row column decomposition is very small compared to the true FFT. What you'll see and maybe at the end of today's lecture or next time's lecture is that if you do true FFT with the true decomposition, you have a slightly lower number of operations, number of arithmetic operations, but implementing that takes longer and is more complex. That's exactly why I can't remember the name of the algorithm that was invented in the 80s. There was a guy at IBM, and it was provably a lot fewer operations than FFT, but it was so complex to implement that nobody ever used it. I have to remember that. Oh, Winograd. Oh, that's it. Winograd transform. He came up with that approach. Okay. So how does the row column decomposition work? Well, you rewrite this equation that you have up here as follows. You can write x of k1 and k2 as summation of n2 from 0 to n minus 1 and n1 from 0 to n minus 1 of x of n1 and n2 e to the minus j 2 pi n1 k1 over n times the other exponentials e to the minus j 2 pi n2 k2 over n. So we call this whole entity here f of k1 comma n2. Why? Because we're summing over n1, so the n1 gets out, and so all that's left is k1 and this n2, because we have to do the summation with respect to that. So basically, pictorially, what you can think of is you start with an n1, n2 array of numbers, it's a 5 by 5 array of numbers, just for the sake of this example. And this is our x signal, and this is our f signal. It's going to be a function of k1 and n2. And what does it say? It says for a fixed value of n2, that means for a fixed row, I'm going to do a one-dimensional DFT of the row, right? This is nothing but a one-dimensional DFT. So I'll take the DFT of this guy, and I plug it into here. And I take the DFT of this guy, and I plug it into here. And I take the one-dimensional DFT of this guy, and I put it into here. Okay? So how many one-dimensional DFTs do I have to do? That's right. So I have to do n one-dimensional DFTs of rows, and each one-dimensional DFT is n points, right? And then after I'm done with that, I have now f of k1 and k2. Stare at this equation. Now k1 is fixed, and I'm taking a one-dimensional DFT of, now k1 is fixed, and I'm taking the one-dimensional DFT for a fixed k1 with respect to n2. So now I'm going to redraw this picture just for the sake of completeness. Can you roll up, please? So this is now my f of k1 and 2. So it's 5 by 5. Now I take a one-dimensional DFT along a column, and now my k1 is fixed, and after I take the one-dimensional DFT with respect to n2, I get k2. So this gets transformed into 5 points here, and this column gets transformed into these 5 points, and this column gets into this 5 points, etc. So in this process, how much work do I have to do? Again, I had to do n one-dimensional DFTs, and each 1D DFT was n point long. So, and how do I do this? So I have to add up this amount of work to this amount of work. And how do I do my one-dimensional DFTs? FFT is just one line of code. And we're assuming that for our FFT, so 1D DFTs, we apply FFT. And we assume that for our FFT, can you roll up, please? We can do n log n type ideas. So we can do n log base 2n mults, and n over 2 log 2n adds, and then adding up everything, this guy, and this other guy that we had up here, adding everything up, you can figure out that you end up with O of, so row column decomposition ends up having O of n squared log 2n operations, which is a lot lower than n to the 4. Operations meaning either mult or add. Okay, it's actually n squared for mults, and then n squared over 2 for adds. I'm going to stop here. So conclusion, this is a lot lower than the direct method. The direct method, by the way, has the shortest amount of code. It's just a do loop, 2 do loops. But this thing is a little bit more work, but not too bad. We managed to decrease the complexity quite a bit. So I'll see you all on Wednesday.